Let's go ahead and work through some of our homework now, starting with the equilibrium ones. So we'll start with the conceptual and algebraic ones. So we have a mobile here showing three different bars with various masses hanging from them. And we want to find the length of segment 1, segment 2, and segment 3 in terms of L, the total length. So I'm going to start with segment 1 here, which is just this lower part. And hanging from segment 1, we have two masses, which means we have a force of gravity here. And also a force of gravity there. I'm calling them the same thing because the masses are equal. And the easiest spot for a pivot here is that point where the string attaches, leading up to the next bar, where there is a force of tension. So I'm going to make that be my pivot there. You probably can figure out that since the masses are equal on each side, that needs to pivot in the middle, which means that segment 1 is just L over 2. But if we wanted to do this a more formal way, we could say the torque from 1 and the torque from 2 must balance. So we could say R1, which I'll say is this distance here, times Fg sine of 90, minus R2, which I'll say is this distance here, times Fg sine of 90 equals 0. Those sine 90s go away, the Fg's cancel out, and we get that R1 equals R2. That's only going to happen if segment 1 is equal to L over 2, half the total length. Moving on to segment 2 here, which is this bar. We have a mass of M hanging from that one side, so that's going to be a force of Fg acting down there. From the other side, it's a little bit trickier. We don't necessarily have a mass hanging directly, but ultimately, that left side is supporting both of those masses. Okay, it's attached to a string, which is attached to a beam, which supports both of them. So in turn, that means there's a force of 2Fg going down here. We have our string pulling up on that middle bar there with a force of tension, and so that's going to be our pivot. Once again, we have two torques created, torque 1 and torque 2, I'll call them. All right, and I can go ahead and set up sum of the torques equals 0 for these. I'm going to define this to be R1 and this distance here to be R2. And so what we're going to have is R1 times 2Fg times sine of 90, that's that first torque, minus R2 times Fg times sine of 90 equals 0. The 90s cancel out, the Fg's cancel out, and what we get is 2R1 equals R2. And so what that ultimately means is, okay, if this length here is twice as long as this length, that means that that segment there, segment 2, is going to be 1/3 the length of the bar. Okay, because if this is 1/3 the length, then this is 2 times that, 2/3 the length, and that means that it adds up to the full length of the bar. For this third and final bar, which is this top bar here, we have a force of gravity acting on the left side of it. Then we have all three of these boxes ultimately being supported by that string on the right side. So we really are going to have 3Fg acting down here. I'm going to place my pivot right here where that rope is and where we have that force of tension going up. Once again, call this torque 1, call this torque 2. Okay, and so sum of the torques is equal to 0. And so I'll say this is R1, this is R2. We're going to say R1 times Fg sine of 90, that's my first torque, minus R2 times 3Fg sine of 90 equals 0. What we end up getting here is that R1 is equal to 3R2. So what that means here is that this segment, R1 here, is 3 times the length of this. R2 is ultimately what we're looking for here. And the way that happens, that R1 is 3 times R2, is if R2 has a length of L over 4, then R1 is a length of 3L over 4, and it adds up to the full length of the bar. You obviously could do this on a much more conceptual level, and that's perfectly okay. If that just makes sense to you, but this would be the more formal way of doing it. For this next one, we have a sign with a mass of M is hung from a massless pole here. It's connected to the wall by a rope like that. So the pole kind of goes up and the sign hangs straight down from that. we first want to derive an expression for the tension in the string. So what I'm going to do is I'm going to write down all the forces that we have acting on our pole here. So we're going to have a force of tension going like that, connected to the wall. We're going to have the force of gravity from that mass acting like that. And we're going to have some force from the hinge, and we'll deal with that question in a little bit. But for now, the hinge is going to be our pivot, and so we're not really concerned with the hinge because it's not going to create any torque. So if we think about our torque, sum of the torques equals 0. Okay, the torques that we have the torque from the force of gravity. Okay, and that's going to be a clockwise torque here. All right, and we have a torque from the tension and the sine, and that's going to be a counterclockwise torque. So it's going to be torque of the tension minus the torque of gravity equals 0. For the tension, actually for each one, we're going to do RF sine of theta. Do it for the force of tension and also the force of gravity. All right, and so when we solve for this, the radius for that force of tension, it acts in the middle of the pole, so it's just going to be L over 2. The force of tension is what we're looking for, and the angle there is going to be 45 degrees. Okay, if this angle here is 45, so is that one, because they're alternate interior angles. If we dust off some of our chemistry skills, minus r, the radius for this force, and that acts at a distance of L from the pivot, times the force of gravity, times sine of 45, and I can get that from thinking about this right triangle here. All right, it needs to add up to 180, so if this is 45, that angle is 90, this one must also be 45. And so that's going to be equal to 0 here. The L's can cancel out, and what I end up, and the sine of 45s also can cancel out, not because they're equal to 1 in this case, but because there's 1 in each term. And so what I end up getting is ft over 2 minus fg equals 0, and that means that ft is equal to 2 times f of g. F of g is just mg, so ft equals 2mg. Part B here asks if the wall exerts a horizontal force on the pole and explain why or why not. So for that, I'm not going to consider my torques here, but I am going to consider my forces. And so if I'm thinking about my forces, the only horizontal forces I have are the force of tension going to the left. But I know that this sine and this pole are not moving at all, so the forces must be balanced. So that means that this wall must exert a force to the right to balance the only other horizontal force, the force of tension, which is going to the left. Second part asks, does the wall exert a vertical force on the pole? And so we're going to think about the same thing here. I'm going to consider what vertical forces we have, and we only have the force of gravity, and so therefore the wall once again needs to create a vertical force here going up to balance the force of gravity so that the net force on the object can remain 0. For this problem here, we have a golf club balancing on a fulcrum as shown, and we can see that the club bounces closer to the head of the club than to the end of the club here. And we're going to then cut the club in half along this dotted line here. We want to know which part of the club will have more mass after it's cut. So there's two ways of thinking about it. We can either think about center of mass or we can think about torques. If we think about torques, we're going to think about the fact that we're going to have a force of gravity on the one side, all right? So I'm going to think about the club, even though it's still intact in this picture, as two separate pieces. So we have a force of gravity acting on the one side and a force of gravity acting on the other side somewhere around in here. Now we don't know it's necessarily in the middle of those sides, but it's probably middle-ish between the two. And so what we see is that the one force of gravity, okay, acts much closer than the other force of gravity. And so in order for those two torques to balance, we must have a greater force here than we do here. And therefore this side, the side with the head on the right, will have a much greater mass. The other way we could explain this would be with center of mass, and it's a pretty similar argument here. But if we think about the part on the left side here, the center of that is somewhere around here. We can assume that the shaft of the club is relatively uniform. And then if we think about the part where the club head is, the center is going to be somewhere in this area. Again, not exact, but we can clearly see that the difference or the distance here, x1, is much greater than x2. And so for the center, where it balances, the center of mass right here, to be closer to this part, it must mean that there's more mass here, because that carries more weight, and center of mass is simply a weighted average. For this problem, we have a system with two masses balancing on a massless beam here, and we want to know the location relative to either end where a pivot can be placed so the beam will balance, assuming the beam is massless. So we could think about torques for this one. I think it's actually easier, though, to consider center of mass here, because all we really want to find is where this system will balance, and it makes it a lot easier to do center of mass if that's all we're concerned with. So we're going to go ahead and set up our center of mass equation. I am going to define a spot to be my 0 point, and I'll just pick the left side to be the 0 point. Although you could have picked the right, it would just change what you base your answer on, whether you're saying it's from the left side, from the right side, etc. So when I go and set up my center of mass here, I know that my one mass is going to be m times the distance, which is 0. Okay, if I'm thinking about this mass here, it's located on my 0 point, plus the other mass, which is 2m, times its distance, which is L, and that's divided by our total mass, which is 3m. That all goes away, and we find that our x center of mass here is just going to be 2L over 3, because those L's cancel out. So there's my answer to A. Moving on to B, if the beam has a mass, will a location where it will balance shift left, shift right, or remain in place? Okay, so if we think about the beam having a mass, right now the center of mass of our system is right about here. Okay, if we add in mass for the beam, that will act directly in the middle. Okay, so that would be the center of the beam, right in the middle of the beam there, to the left of our current center of mass. And so that means adding in that mass there is going to shift that balance to the left some. Okay, because we're adding another mass that's located right here. All right, even if it's a small mass, it still is going to shift it a little bit to the left, because of really what the definition of center of mass is, the average location of the mass in our system. So we're adding more mass to the left of our center of mass, it's going to shift the center of mass to the left.